Okay, class. Hi. Let's go ahead and dive into the first sort of material. We're going to be in Chapter 2. Chapter 1 just gives some basic definitions. Chapter 2 is where it introduces ideas about atomic bonding, and a lot of this is stuff that you probably should have seen in general chemistry, so a lot of it might be review, and that's okay. Okay, here's our learning objectives. I'll try and start every class with some learning objectives. These are useful because then when it comes time for tests and things, these are things that you should definitely be able to do. And if you don't know how to do those, if you need some help, that's when you want to come and talk to a TA or myself and we can review things. Okay, so the learning objectives for what we're going to cover today is first, I'd like you to be able to describe basic atomic theory. We're going to talk about shells of electrons, about valence electrons, ionization energies, things like that. Then, I want you to be able to calculate the energy and therefore the wavelength of radiation emitted or absorbed as electrons transition from different states to one another. Okay? We'll actually use this to describe something called EDS calculations. The third thing is I want you to be able to relate interatomic forces to real materials properties, things like stiffness, melting point, and thermal expansion. And lastly, I want to review bonding and calculate bond character from electronegativity. Okay? So again, a lot of this stuff is things that you should have seen in your Gen Chem 1 class. If you've taken Gen Chem 2, great, but this is Gen Chem 1 stuff. Okay? So we're going to kind of go through it as a review. We'll do it pretty quickly, right? So structure and bonding, they are important to cover because they lead to everything else in material science. So much of material science is built on bonding, and so we have to have a pretty good understanding of it, right? For example, why are noble gases gases instead of being solids? You know, why are some things soluble in water, but other things might not be, right? For example, sand won't dissolve in water, but salt will, right? So why? What's the difference there? It helps us answer questions like, why do some things melt at low temperatures, whereas other things only melt at high temperatures, okay? So we need to understand it, and I'll give you some examples as we go. Let's start with some of the most fundamental stuff. You know, what is in an atom? An atom has, you'll remember, protons and neutrons. Those exist in the nucleus. So you've got this positively charged region, right, made up of protons and neutrons. Protons have a positive charge, neutrons don't. Both of these are relatively heavy compared to the things circling around them, which are your electrons, okay? And in the early days, they didn't understand much about this, right? They were vaguely aware that there was positive and negative charges, right? But they certainly didn't know how heavy these things were. They didn't know where they were distributed or a lot of things like that. And so some of the very first work that happened at the turn of the 19th century, right, the end of the 1800s, the beginning of the 1900s, was really delving into this basic stuff. So if we go way back, some of the people that were important in this area were people like J.J. Thomson, Robert Millikan. You probably learned about some of their work in your Physics 1 class. Maybe you're taking that at the same time as this class now. If so, that's fine. For example, Robert Millikan's oil drop experiment was really influential, and it's pretty amazing. He basically took this apparatus that he could sort of spray and make a mist of oil droplets. Okay, as these things were falling down, there was a little gap, and as they would fall through that gap, there was an electric field. Now, since these particles have charges on them, if you apply an electric field, they should resist that motion. And so he found that if he tuned the electric field just right, and you looked through this with a microscope, he could make these little oil drops hover in space, right? And since he could measure how big of a glob it was, he could estimate how many electrons were there, and from the applied electric field, he could actually estimate the charge to mass ratio for these materials, right? So this was huge. This was a big discovery. All of a sudden, we know what the ratio is of the charge of an electron to its mass, okay? Now, at this time, we still didn't know that nuclei existed, right? They figured that they could charge these things. For example, if they put it in a magnetic field and then they applied an electric field, they found that depending on the way that they could charge this thing positively or negatively, they could deflect electrons traveling through here upwards or downwards. So they knew that they were charged because they could change the direction in which they traveled by switching the field they passed through. But they still didn't know anything about where the positive charge was coming from. They said, okay, these things must be negatively charged or we wouldn't be able to move them up and down in an electric field. So if they're negatively charged, what is positively charged? And in the early days, they had this sort of plum pudding model, right? Plum pudding model where they assumed kind of incorrectly that the nucleus wasn't at a single point, but rather that it was sort of dispersed throughout. We'll learn that that's wrong, right? You probably remember it. Something that I think is really cool is that this guy, Robert Millikan, so cool. He was at, I don't remember if it was Yale or where, but it was in the early days. and they needed somebody to teach physics, and he didn't study physics. He studied classics, Greek and Latin, right? And so they asked him as a graduate student, they basically said, we need somebody to teach physics. Are you willing to do it? And he agreed to do it because he needed the money, I guess. And so this is what he said about it. Like, imagine yourself in those shoes. Imagine that you've never even taken physics before, and now you're expected to teach as a graduate student in this class. He says, I doubt if I have ever taught better in my life than that first semester of physics in 1889. I was so intensely interested in keeping my knowledge ahead of that of the class that they may have caught some of my own interest and enthusiasm. And gosh, I really hope that you guys feel that way. Like, I've taught this class 6 times now, so it's getting to be comfortable, but I still love coming up with ideas and things that are going to help you guys learn things a little bit better. So if you have questions, it's going to make the class even more exciting and interesting. And so as soon as I'm back and not doing these online, I would love to have you interrupt me and ask questions in the middle of class, and that'll be fantastic. And in the meantime, go ahead and post things to Canvas and the Piazza discussion board, and we can answer questions there. Okay? So this guy, these are all Nobel Prize winners for discovering the electrons, for discovering their charge. We know that the plum pudding model, where positive charge was sort of everywhere with electrons sort of like raisins or plums in your pudding, right, was wrong. We know this because Rutherford did his famous backscatter experiment, where he basically had this particle emitter. So he's launching particles at this gold foil, and the vast majority of them go straight through the foil. But every once in a while, they would get deflected, and some even got bounced straight backwards. And the fact that they're getting straight backwards, that must have meant that there was a very small but extremely positive charge in one point in the atom, as opposed to lots of little ones. I mean, he described it, I can't remember his exact words, but it was something like if you had a battleship with one of their massive cannons shooting a piece of tissue paper and then having it bounce back. That's how surprised he was that any of these should bounce back and be measured, right? So that led to us understanding that not only are there positive and negative, we knew something about their charge, but we know that the positive is really just in one small spot in the atom, that most of it travels right through and only occasionally does it bounce back, right? All right, the next big discovery that we need to sort of talk about had to do with electron energy levels. So if you go back before, our negative electrons are just sort of everywhere in this plum pudding model, but soon we realized that they actually occupy discrete little bands that are sort of like Russian nesting dolls. They sort of stack on each other. And the way we learned that was by comparing light coming from specific elements from black body radiation. So black body radiation, that's kind of like the sun. Is the sun black? Well, in any case, like a tungsten light bulb. If you just emit light at very high temperatures, it's white light, and so it covers all the different radiation wavelengths. However, if you take specific elements and you look at how they burn, you can see that they actually emit light at very specific lines, very specific wavelengths. A little bit of red, a little bit of yellow, some of these. And each element was different. So when they realized this, they said, aha, so every element, it must have first off, discrete energy levels, and they're unique to one another. So that led them to start theorizing that, okay, like in the Bohr model, it basically said, like, we know that we have this positive nucleus, and now you've got shells that electrons can occupy, and as you jump between these orbitals, going up or going down, as you go down, it's going to have to give off energy, right? So it gives off a wavelength of light of a very specific wavelength. That might, for example, be one of these red stripes or yellow or something like that. Okay? And when it absorbs energy, it's going to absorb energy of a very specific energy, right? So a photon's going to come in and get absorbed to go from one energy level to another. Okay? So we now understand this better. It's not just these simple shells, but they're sort of subshells. And again, if you've taken chemistry, you've seen this before. You know that there's like the 1s electron orbital, the 2s orbital, the 3 2p orbitals, the 3s, the 3p orbitals, the 5 3d orbitals. Each one of these can host 2 electrons, right? So this is hydrogen, helium, beryllium or lithium, I forget the periodic table. It's lithium, then beryllium, then you've got, let's see, boron, carbon, nitrogen, oxygen, fluorine, right? That's what leads to the periodic table, was this sort of understanding. And you can transition between all of these levels. Now, some of those are really small changes in energy, and some of those are big changes in energy. But that's all what these different spectral lines are indicating. Okay? All right. Now, another thing to remember is that the shapes of these orbitals, even though we've drawn them here as circles, they're not all circular. Only the s orbitals are circular, right? So here's our s orbitals. If you look at the different n levels, n equals 1, 2, 3, 4, 5, 6, and those again correspond to our periodic table, which we'll pull up real quick. Okay, in our periodic table, each one of these rows, right, as we go down these rows, those represent different quantum numbers n, the principal quantum number. So this is n equals 1, n equals 2, n equals 3. This is why we call these the 1s1 electrons. These are the 2 s electrons. These are the 2 p electrons, 3s, 3p, and so forth, right? So the s electrons continue being spherical in shape, but the p orbitals, right, these things are dumbbell shaped. They go in the z direction, in the x direction, and in the y direction. So they're sort of like this and in that direction, and they're sort of dumbbell shaped. And then the d orbitals get sort of funky shaped. The f orbitals get even weirder shaped, right? But that's the shape of these orbitals. So it's wrong to think of them just as spheres. We draw them as spheres, but in fact realize that they have these more complex shapes, which leads to important other properties that we won't get to in this class. I don't think we will. Okay, so they started understanding that there was these different levels, right? And that you could transition energy between these things. People started around this time investigating ionization energies. So what is an ionization energy? Well, when you ionize something, you make it charged. So as a neutral species, lithium as a neutral lithium metal, it costs energy to strip away an electron to make it go from lithium metal to lithium ions. For example, if you've got lithium and you turn it into lithium plus by pulling off one of its electrons, that costs some amount of energy. And that's what this ionization energy is measuring. And what they found, so here's your ionization energy as a function of atomic number, is that it wasn't the same. In fact, it had this weird periodic dependence, right? It went up, then it dropped. It went up and it dropped. It went up and it dropped. And then even it started doing weird things in the middle. It would go up, but then it would stagger and then increase. It would go up and stagger. Here in the d electrons, it would go up, do something weird in the middle, right? And so they were scratching their heads. The periodic table wasn't yet well understood, but this started helping them understand why it has the shape that it has, right? You started seeing basically 1, 2, that's in your 1s, then you have your 2 s's, then you had 6 more for your p's, okay? And we're not going to get into the quantum numbers in this class because you've seen it in Gen Chem already, but I'm just reminding you that this is sort of where this is coming from, and that this ionization energy can be thought of as an energy required to strip away an electron. This is important because some things really don't want to lose an electron, like fluorine. Fluorine's right here. Now remember this final column on the end, that's our noble gases, and that's when they have a filled shell of electrons. So its outermost shell is totally filled with electrons, and it's very happy. It would like to stay that way. So fluorine is 1 electron away from being there. So is it going to be happy if you try and take one of its electrons? No, not remotely. It's going to hate it, right? So it has a very high cost, right? If you look at where fluorine is, right next to neon, right? So neon costs the most. It's already completely happy. Try and take one of its, and it's very upset. Fluorine's right next to it. It really doesn't want to lose it. Whereas other things, like say sodium doesn't care. Sodium's clear down here. It's only 1 electron. If you take away an electron, it looks like neon. It's much happier. It has a filled outer shell. So it didn't really want these outer, or what we call valence electrons, very badly. And so they cost less energy to strip them away. That whole concept of valence electrons, the ones that are outside of the filled shell, become really important because they help us understand bonding. For example, if you've got titanium, how do you know what sort of common oxidation states will it have? Is titanium going to be commonly 1+, right? Or will it be titanium 2+? Will it be titanium 3+? Or titanium 4+? Okay? Or something else. Well, let's just start counting, right? So its outermost electrons, in order for it to look like argon, it could lose 1, 2, 3, 4. So sure enough, a common oxidation state for titanium is 4+. Okay? Now it can take other states, but a common one is going to be to get rid of all of its valence electrons. Okay? And that's a pretty common theme. Chromium is very commonly, 5 or 6+, right? And they can take other states. Now, when I get back to class on Friday, I'm going to give you all a really nice periodic table which tells you some of the common oxidation states. And that helps you kind of understand which electrons it's willing to get rid of. So we'll talk about that more, I think, on Friday when I get back. Okay? This, in the early days, led them to understand something called the Rydberg formula. I'm going to write it out. So it says that 1 divided by the wavelength of light given off, when elements, if you've got these different transitions from one state to another, then the Rydberg formula said that it's equal to the Rydberg constant multiplied by 1 over n1 squared over 1 over n2 squared, where n1 and n2 represent these different orbitals that you're transitioning between. Now the big caution I have to give you guys is that this only works for hydrogen. This does not work for any element, right? Each element is specific because the Rydberg constant was specifically made for hydrogen. If you try and use this for helium or lithium or sodium or whatever else, it's not going to work. You have to modify it. So they have to put like an additional term in front of the R to make it work. So that's not super helpful, right? But it does at least explain some of the principle as you're jumping between these different levels, how you might be able to start to calculate this energy, okay? The radiation that's given off, we can refer to it as an energy, but we can also refer to it as a wavelength. Now, how can we do that? Like when they say that a photon coming off has 500 nanometer photon, wavelength, or that it's some energy in electron volts or something, what are they talking about? How can you convert between those? Well, there's an expression that you would have seen in Physics 1, or maybe you're seeing it now. We'll introduce it for you here. You can convert between energy and wavelength with this formula. So it goes like this. Energy is equal to H times C divided by lambda. Now, if you are a fan of Stranger Things this semester, maybe plug your ears because it's a bit of a spoiler. But if you remember Susie from Utah, she exists. And when they have to remember the code to get into the Russian password protected thing, I don't remember what it was, they had to remember Planck's constant, right? And remember, Susie made him sing the song. It was amazing. And then she said, Planck's constant is 6.626, what have I got it? 626070004, which is wrong because that's not the answer. It's actually that times e to the negative 34 joules times seconds because units matter, as we will learn in this class. Now, that is joules times seconds. But when we're talking about energy differences on an atom basis, it makes way more sense to convert that into electron volts. So here's Planck's constant for us in electron volts, okay? So now that we've got Planck's constant, we know that the speed of light is 3 times 10 to the 8th meters per second. If you take that, that allows you to convert between energy and wavelength, right? So in this class, we will do many clicker examples, right? Where you're going to actually be able to do questions in class to make sure you understand things as we go. And it's the first day of class, and I'm not even there, so we're not going to do this for real. But this would be what a practice clicker question might look like. Okay, I would say that the following. A green laser pointer has a light with a wavelength of 525 nanometers. What energy does this photon have? Okay, so how do you figure out the energy of that photon? Well, we're going to use our equation. We know that E equals hc over lambda. And we're given lambda, right? Because we're given a wavelength. That is lambda. So we're going to write this out. We're going to say that this is equal to 4.135 times 10 to the negative 15th eV times seconds. That's going to be multiplied by 3 e to the 8th meters per second. So our seconds are going to cancel out. Then we're going to divide that by a distance, right? 525 nanometers. Now, what is a nanometer in meter? That's just equal to 10 to the minus 9th meters. So if you look at this, our seconds cancel out, our meters cancel out, and we should get our answer in electron volts. Okay? So when I punch that in, I find the following. 4.135 e to the negative 15th times 3 e to the 8th divided by 525 e to the negative 9. I get that that's equal to 2.36 electron volts. Okay? So if you haven't used units in a while and you can't remember scientific notation, you're going to want to review those. The TAs are going to be super helpful with that. So ask them about it and they'll review it and you'll be good to go. Okay? So in a clicker question, you might actually type in the answer, or it might be multiple choice or something like that. But that's typically what a clicker question will look like. So we've already talked a little bit about oxidation states. I'd just like to point out that multiple oxidation states can exist, right? For example, take FeO. If you have a compound that has an Fe2 plus oxidation state, we know that oxygen is almost always 2 minus. So Fe2 plus with 1 oxygen 2 minus, that's going to lead to a stoichiometric 1-to-1 ratio. 1 iron for every 1 oxygen. This thing's 2 plus, this guy's 2 minus, okay? Now, iron can also be Fe3 plus. It can lose 3 electrons. So in that case, something like this, right? You've got minus 2 and you've got plus 3, right? Oxygen's always minus 2. In this case, iron's plus 3. So you've got negative 2 times 3 is negative 6. And then positive 3 times positive 2 is 6. So overall, the charge is balanced. But you can also have mixtures, like in magnetite. This was like the very first compass material, right? The needle in the very first compass that like ancient mariners used. This is a naturally magnetic material. Is Fe3O4 magnetite. It is made up of Fe2 plus and 3 plus. The reason we know that is because, again, you've got minus 2 from your oxygens. So that comes up to a negative 8 charge since there's 4 of those. So we have to get to a positive 8 charge, but we do that from 3 different atoms. 8 divided by 3 is not a whole number. So it must be a mixture. In fact, it is. 2 of the ions are 3 plus, and 1 of them is 2 plus. Okay? So you can have compounds where you have mixtures of valence. Okay? How does electronegativity change across the periodic table? So what is electronegativity? Electronegativity is how badly an element wants an electron. So remember, go back to our ionization energy plots, and we said that things like fluorine really wants to pick up one more electron because then it will look like neon and be happy, whereas sodium would pretty much not want that extra electron. So we would say that fluorine has a high electronegativity and sodium has a low electronegativity. So we know for one thing that electronegativity, we'll call it chi, is going to increase that way, but it's actually going to increase that way. And if you don't remember why, it has to do with something called shielding, where, take cesium. Cesium has 6 different principal numbers, right? So it's like many of these Russian stacking dolls. And so what happens is that even though it has a big positive center, it's shielded by lots of these layers around it, right? So if you look at it, you've got lots of these layers, and I'm drawing these simplified, but the outermost electron is really shielded, and so it doesn't see it as much, and so it has a lower electronegativity. So that's the sort of trend as it kind of goes up and to the right. Okay? All right. Now how about this? Why do bonds form? Why do bonds form, right? We know that some things exist bonded and some things don't, right? For example, helium, is that bonded? No, it's just a helium gas ion, an atom, right? But other things like oxygen, we always think of oxygen as O2, right? So why does oxygen bond but helium doesn't? Okay? What's helpful to think about that is these bonding diagrams. And again, this is stuff you'd seen in Gen Chem, so I'll just review it here. But let's draw up oxygen. So where is oxygen? Oxygen is right here. It's got 8 electrons. It fills its 1s. It fills its 2s, and then it has 1, 2, 3, 4 electrons in its 2p, right? So 1s, 2s, and then you've got your 1, 2, 3 orbitals in your 2p, right? So that's 2p, 2s, 1s. Oops. So you've got oxygen here with 8 electrons. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. Now, we know that it does this because electrons are just like people. Electrons are like people sitting on a bus. People don't like to sit next to people if they can help it. So when you start to fill these orbitals where you've got 4 electrons and you have to start filling them up, the very first thing they're going to do is go 1, 2, 3. And then it's got that 4th electron. Only then will it pair up, just like people on a bus. They will sit one person per bank of seats until they have to start pairing up, unless they're a weirdo. Don't be the weirdo. Okay? So that's going to be them. So that's one oxygen. Now, if nearby we've got another oxygen atom doing the exact same thing, filling up its 1s, 2s, and its 4 electrons in its 2p orbitals, now consider the bonded one, okay? In the bonded one, we're going to bring these 2 orbitals together. We're going to bring these 2 orbitals together. And we're going to bring these ones together. And I have to draw it correctly. We form a bonding and anti-bonding orbital. So hopefully you remember some of this from Gen Chem. These bonding and anti-bonding orbitals. But now consider what it does, okay? We've got 8 electrons from each oxygen, right? This guy had 8 electrons and this guy had 8 electrons. So let's start filling them up. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? Now overall, if this is like where the average energy was before, we actually have more of our electrons occupying a lower energy level, right? Because energy goes up in the y direction here. And so by bonding, by going from an individual O oxygen atom to an oxygen molecule, as two O atoms turn into an O2 molecule, we actually go down in energy. In energy, it gets stabilized by 5 electron volts per bond. So in other words, to break this oxygen molecule, if we wanted to break it and turn it into individual oxygen atoms, we would have to put in 5 electron volts to break that bond, because these things are stabilized by about 5 electron volts, which is pretty cool, right? So if I told you that something else had an electron volt bond, the bond of something else was 10 electron volts, like I think nitrogen N2 is something like 10, that's going to be a harder bond to break. And sure enough, it is harder to break nitrides. Even though our air is mostly nitrogen around us, like we're breathing 21% oxygen and 78% nitrogen, nitrogen doesn't bond with things nearly as much. It's mostly inert because it's more strongly bound. And that's a good thing, because we need oxygen to bond to things, or everything would be different in this planet. Okay? Now, let's switch gears and let's talk about a lot of the properties that we care about by thinking about bonds as the result of attractive and repulsive interatomic forces. Okay, so let's draw this out. So we're going to draw here. This is interatomic separation. Interatomic separation, which I'm just going to call R. Okay? Now on the y-axis we've got force. So on the positive versus negative, we're going to call the positive side an attractive force. And then on the negative side, we'll call that a repulsive force. Okay? So if you have an atom, let's talk about ions for a minute. Let's talk about salt, right? So you've got salt. So salt is made up of sodium chloride, where the sodium is plus and the chlorine is minus. The reason that's the case is because sodium really wants to get rid of its electron, because remember, if it loses one electron, it looks like neon and it's happy, so it becomes positively charged by 1. Meanwhile, chlorine would love to pick up one more electron, because then it looks like argon, so it absorbs that electron and becomes 1 negative, okay? So you've got sodium and chlorine. So as these things get close together, what do we know about positive and negative? Is that they attract, right? Opposites attract here. And so how do they attract? Again, if you've taken physics, you would have known that they attract, and the attraction looks something like 1 over R. And we know that because the force of attraction, force equals K times Q1, the charge of the first atom, times Q2, the charge of your second atom, all divided by R squared. Hopefully you would have seen that at some point. That's called Coulombic attraction. That's the equation. And so K is equal to this constant. It's equal to 1 over 4 times the permittivity of free space. Hopefully you've seen that in physics. But in any case, when we plot it against R, it should have this 1 over R squared sort of dependence. Meanwhile, when you bring atoms closer and closer together, they can't just get infinitely close together. Why not? So the reason that they can't get infinitely close together is, you remember, our atoms are made up of lots and lots of shells, of stacked shells filled with electrons. So if you bring 2 of these close together and they start to overlap, then you're forcing all of your electrons to occupy the same volume of same space at the same energy. And that violates the Pauli exclusion principle. From quantum mechanic reasons, which we're not going to cover in this class, you cannot do that. You can't have electrons occupying the same volume of space at the same energy level. It's not allowed. So instead they have to go to higher energy levels. So what that means on a force diagram is that it's a really steep penalty. Sometimes they call it a hard sphere model. Basically, there's no penalty until you get close, and then there's a huge penalty. It takes off really fast, right? So what we're going to do is we're going to add these two together, okay? So the net energy, I'm going to call it Fn, is going to be equal to the attractive force plus the repulsive force, right? So the blue line and the red line, if you add those together, you're going to get something that would look like this, okay? Where you're going to have a point at which there is no net force. If there's no net force acting on an object, you are in equilibrium. When F net, well, I'll just call it Fn just to be consistent. When that's equals 0, that's when you have no net attractive force, therefore it must be in equilibrium. If there was a force on it, they'd be either getting closer together or further apart. But since there isn't, it's just going to stay put there, okay? Now, it's useful to think about things in terms of forces, but it's also really useful to think about them in terms of energy. So, quick question, how do we relate forces to energies? Remember, if you think way back to calculus, hopefully you saw this, or physics. Well, we know that energy is equal to the integral of force over distance. E equals the integral of F dr. Or, alternately, force equals the derivative of energy with respect to distance, okay? So, we can use those to go ahead and redraw this figure, but on the y-axis, instead of it being force, we can make it energy. So let's go ahead and do that. So I'm going to redraw this. I'm going to make it try and line up. So you've got your line right here. This was our equilibrium point. I'm going to keep that. That's our point of equilibrium. So the x-axis is still the same. That's still our interatomic separation distance. But this time our y-axis represents energy. Okay? Where you've got positive and negative energy. Okay? Or in other words, this is higher energy, which is not desired, and this is lower energy, which is desired, right? Things can lower their energy, they're going to do it. So, what do we know about this? Well, if force is the derivative of our energy expression, then that means if we were to take the derivative of it and it's negative down here, right? From here until that point, it's negative. That means that our energy expression is decreasing. Remember this from calculus? Hopefully you've seen this before. So I'm going to draw it. Our energy expression must be decreasing until that point, right? At that point, when it's equal to 0, now it's positive. So it's going to continue increasing all the way out to infinity, but it increases quickly and then it starts to slow down. So our energy does something like this. Okay? So that's our net energy. Okay? That's the net energy curve, which, again, net energy, we could say that it's equal to an attractive energy plus a repulsive energy, just like before. So we're going to write this out and say that it's equal to negative A divided by R to the M plus B divided by R to the N. Okay? Where again, this time, this was our attractive energy. And then the other one, this represents repulsion, because one's positive and one's negative, okay? So the overall energy is going to be a combination of these two things. But this sort of curve, we call this the potential energy well, right? Because it's sort of spherical, as if it was like a well that could hold water. This is extremely useful. It's extremely useful because this helps us explain lots and lots of things. For example, let's draw a few. It tells us the binding energy, meaning if you have two atoms and they're some distance apart and you want to pull them all the way apart and totally separate them, we call that melting, right? It went from being a solid that was bound together and you completely separate them, that's melting. In order to do that, you have to move it all the way up to infinity away, or in other words, you have to overcome this distance. You have to go up that much distance. So that E naught, that's your binding energy. It's how tightly things are bound together. Remember, like this oxygen molecule we said that was bound at 5 electron volts? Basically that means that the depth of this well for 2 oxygen atoms being bonded together to make an oxygen molecule, it's 5 electron volts deep. Because an electron volt is a type of energy, right? You could write it in joules or whatever else you want, but electron volt is a convenient one because it's 5 instead of some crazy number, okay? So that's one thing this can give us. Other things it can give us is really cool stuff like thermal expansion. Here, let me draw another one of these. I'm going to draw it with a couple different materials. Okay, you tell me which one's which. So again, this is energy versus separation distance. I'm going to draw 3 curves here. One looks like this. One looks like this. and one looks like, running out of colors, that. So if I said that one of these is a metal, one is a ceramic, and one is a polymer, which one's which? First off, a polymer is a plastic, right? So metal, ceramic, plastic. How would you go about thinking this? Well, first off, we know that the binding energy, this depth of this well, that's related to the melting point, right? If it's really hard to pull these things apart, it's going to be deep. So which one melts at the highest temperature? A ceramic, a metal, or a polymer? Hopefully you said a ceramic, right? So since this one is the deepest, that must be our ceramic. Then metals typically melt at slightly lower temperatures. So this is probably our metal. And then the green one is probably our polymer, right? So these will look different for different classes of materials. Something else that can tell us is thermal expansion, right? So let's just look at one of these for a minute. So if we look at just one of them, we're going to redraw it. Energy versus interatomic separation. I'm going to draw our ceramic. Now the ceramic does something like this. Okay? Notice that this is an asymmetric potential well. It's not like it's a perfect U. Like a perfectly symmetric one would look like that, right? It would go up and it'd come right down. Ours doesn't do that because the radial or the radial dependence of these two things is different. One goes as 1 over r squared and one is r to a higher power, like r to the 8th or 9th. Okay? So it's not symmetric, it's asymmetric. So imagine that you're at your bonding point, R0, equilibrium. So again, when do we have equilibrium? When F0 equals 0. This happens when R is equal to a special number that we call R0. So this right here is R0. Right there, R0. That's the bottom of the potential energy well. Okay, so again, that happens at R0. Okay? Now, if you are right here, an atom, and you take it all the way to absolute 0, you cool this thing down so there's no thermal energy, then you will stay right here. Your two atoms are going to just be locked next to each other. But if you start to warm it up a little bit, you start to give it thermal energy, then you're moving it, you're giving it the ability to occupy these different areas. Like it can basically slosh back and forth like that. So this helps us understand thermal expansion, right? If you heat this thing up and you're giving it more and more energy, so temperature is increasing as you move up that way. Look at the average position. The average position of this, if I'm just drawing it right in the middle of the red lines, the average position is moving away. Like your atoms were initially this close together, and as you heat it up, they start to move apart a little bit, right? Because you're giving it thermal energy, and it can occupy some average separation distance, because it's rattling between these things. It's on average getting further and further apart. So that is your thermal expansion coefficient, right? The expansion of, your coefficient of thermal expansion tells you how much a material expands when you heat it up. That literally comes from these drawings. And so a ceramic that has a deep potential well has a more symmetric potential well. Let me write this down because it's important. The more symmetric the potential well, the deeper it is. Or the other way around, the more shallow a potential well, the more asymmetric it is. And I definitely spelled that wrong. Okay? Therefore, would you expect, going back to this picture for these things, which would you expect to have the highest thermal expansion? A ceramic, a metal, or a polymer? Well, the ceramic is the deepest, it's the most symmetric, so it's not going to expand as much. A metal, it's going to expand a lot, more than a ceramic, but not as much as a polymer. And a polymer is going to expand like crazy. And sure enough, if you look at average values of these things, this thermal expansion coefficient, let me change the color on these real quick. So the thermal expansion coefficient, we'll call it alpha. That's a typical term for it that they, the typical variable that they use for it. Okay, we would say that thermal expansion coefficient for a polymer is something like typically over 100 parts per million per K. Right? Parts per million, that's just like saying percent. Percent is like parts per 100. ppm is parts per million. Okay? Now let's compare that to a metal and a ceramic. The coefficient of thermal expansion for a metal is going to be something like maybe 50, let's even call it like 10 to 100 ppm per K. And then the coefficient of thermal expansion for a ceramic, okay, that's going to be typically less than 10 ppm per K. So see how this is useful? Bonding actually tells us something useful. Like bonding, because we know how it leads to these shapes and why these are different, because things are bonded more tightly or less tightly, that leads to some really important things like why things expand at different rates. It also tells us things about the stiffness of materials, right? So the stiffness, how could we use this to get stiffness? Well, stiffness, think about it in terms of force. A material that's really stiff means that when you pull on it, like you're pulling on it or squeezing it together, a stiff material, will it deform a lot or a little? A stiff material, if you pull on it, it won't deform very much. So think about this. I'm going to redraw it. Let's go back to our force diagram. Okay. If we go back to stiffness, we're going to draw our force diagram. Here's the net force point. So you've got this sort of thing happening. Again, that's interatomic separation. This is force. So if it's at its equilibrium point, if you took the slope of that, that would tell you how stiff it is, right? That'd be proportional to the stiffness anyways. And so the different slopes here are going to be proportional to what in terms of energy? It's going to be in terms, since this is the derivative of energy, right? It's going to be, since this is the slope of the derivative, that's the second derivative of energy. What's the second derivative of energy? It's the curvature. It's the radius of curvature, right? So I'm going to write this out. The Young's modulus, which we'll just call stiffness for now, but the word that we're going to learn later on this semester is Young's modulus, E sub y. That's going to be proportional to 1 divided by the interatomic separation distance, right? The average, what we call equilibrium bond distance, multiplied by dF over dr. That's the integral of your force expression evaluated at r equals r naught. Right? So that'll give us stiffness. So again, if we go back to these three materials, ceramic, metal, and polymer, which one has the highest radius of curvature? This guy. Which one has the lowest? That guy. So which one's the stiffest? Well, we know that the one that's the stiffest should be the one, some bond distance, right? The average bond distance multiplied by the radius of curvature. So ceramics are definitely going to be the stiffest. Polymers are going to be the least stiff, with metals being somewhere in the middle. And that turns out to be true. Okay? So in the homework, we give you some chances to work on equations like this. For example, we have you calculate the energy expression if we give you the force expression. Let's say we give you this equation. The net force is equal to two terms, the attractive and the repulsive. We have you figure out how to get the energy from that. And how do you do it? You just take the integral with respect to r, right? Or maybe you go the other way. Maybe we give you energy, we have you take the derivative, and that gives you the force expression. We have you set the force equal to 0, the net force equal to 0, solve for r, and that gives you r naught. So you'll get a chance to do this on some homeworks. Go ahead and come to class on Monday and Wednesday, and my TAs will be there, and they will just work a couple examples of this. I think it'll be really helpful because there's a bunch of these on your first homework, which will be posted, by tonight probably, before the weekend, before school starts. Okay, so that is some of the things that you can do with these. Right, you can get coefficient of thermal expansion, you can get stiffness. The binding energy, we already talked about, like how deep this potential well is. That's going to be proportional to the melting point. So you are already getting 3 really important properties out of materials just from thinking about bonding, okay? Which is pretty neat. Okay. So we'll probably talk about this as a quick review when I get back on Friday, or with the TAs, they can talk about this as well. So we've already talked about thermal expansion, we've talked about stiffness. Something I want to introduce now, we're going to cover it later on in the semester, but it's at the very end, and we're going to use it before then, is something called the rule of mixtures. So let's say you have two properties of something like density, right? The density is the mass per volume, right? Density equals mass per volume, where this is called density, and we use the Greek symbol rho for it typically, okay? If mass is that's equal to mass per volume, when you have a composite material, there's something called the rule of mixtures, which is a really good way to estimate things. It doesn't always work. It is just an estimate. But if you wanted to make the estimate like of the density of something, the density of a composite, if you wanted to estimate it, then it would be equal to the volume fraction of phase A times the density of phase A plus the volume fraction of phase B times the density of component B. I wanted to introduce that now in this very first chapter because we're going to use it a fair bit, and some people might not have seen it before. It's kind of intuitive, right? So if you have like, this is your whole material, and phase A makes up maybe 10 volume percent, and then phase B is 90 volume percent. If you know the density of A and B, then you could estimate what the overall density is, okay? All right. So when it comes to forces and bonding, you've got different types of bonding. You've got ionic bonding, you've got covalent bonding, right? So if you go back to chemistry, what is an ionic bond versus a covalent bond? Well, we already gave you one example. We said salt. Salt had this sodium, which was happy to get rid of its electron, and chlorine was happy to receive it. If they basically give the electron away, remember that is an ionic bond, meaning there's a big difference in electronegativity. Chlorine has a high electronegativity, sodium has a low electronegativity, and so because of that big difference in electronegativity, it tends to be ionic bonding. The electron's just given away. Other things like carbon bonded to carbon, first off, carbon's like in the middle. It's 4 away from a full shell, and it's 4 away from getting rid of a full shell that way. So does it want to get electrons or get rid of them? It doesn't really care. In fact, it's more likely to share electrons. So carbon is more likely to bond with 4 other carbons, and in doing so, it'll share one of its electrons with 4 other, and so overall, they all have completed outer shells. So if there's sharing of electrons, that's a covalent bond. Okay? And again, you've seen this stuff in Gen Chem, so I'm going fast through it. I'm going to skip Lewis dot structures. What I really want you to remember is that there's other types of bonds. There's metallic bonds, right? In a metal, like nickel metal, it's not that it's trying to turn into krypton. It's just that on average, you have a bunch of little positive nuclei that are positively charged, and you have a bunch of electrons. It looks a lot more like the plum pudding model that we talked about, actually, right? It's an average sharing. And then you've got van der Waals bonding. And van der Waals bonding is secondary bonding, meaning it's not even a full electron typically. It's like fractions of an electron. So water is a good example, right? If you take water, H2O, when you draw that, its Lewis dot structure actually looks like this. H is bonded like that. And so it has these extra electrons that are just what are called lone pairs. They're not involved in bonding, right? Oxygen just has them. And then oxygen wants electrons more than hydrogen does because it's more electronegative. So there's an overall negative charge here and an overall positive charge over here. So if you've got another water molecule nearby it, think about what's going to happen here. That one is going to have an overall negative and an overall positive. So look what just happened. These two interact with one another. It's not a full electron difference. It's like a slight. It's like oxygen kind of wants it more than hydrogen, so it's not a full. It's not like oxygen has the electrons. It's just a little bit more. But this interaction, that is a van der Waals bonding. It's a specific type. It's called a hydrogen bond, right? Which is when it's with water molecules. But anything can have that. You can have polymers, which we'll learn about are chains, and these can have a slight negative. And so if you have another polymer chain which has a slight positive, again, those can interact, and that is van der Waals bonding. In fact, that's the bonding that holds polymers together, right? That's why they melt at such low temperatures, is because this is a weak bond compared to ionic and covalent, which are much stronger bonds. That's why polymers melt at low temperatures, is because this is a weak bond. It's not really holding an electron in place. It's just like fractional electron charge, okay? Now, you can calculate how much ionic versus covalent. There's a helpful formula, which is 1 minus the exponential of negative 1/4 multiplied by chi A minus chi B, where chi is the electronegativity. Okay, and then this whole thing multiplied by 100%. That will give you the percent ionic bond, right? So this electronegativity, you can find that in your book, the table in the book. You can also Google it. Yeah, so here you see this is showing the electronegativity for a periodic table. And again, things like fluorine has the highest electronegativity value of 4, whereas things like cesium, it's got that one extra electron and it's heavily screened because it's down low on the table. It's really low. Now, you're going to want to use the values that are in the book because that's what we're grading off of. They're going to be pretty close. It's not going to change it very much, but that's what you could use to calculate the percent ionic character, right? This will tell you to what degree is it ionic, okay? So that is the first chapter. Again, come to class on Monday and Tuesday, or Monday and Wednesday, and the TAs are going to go over some helpful problems because doing these transformations between energy and force, it uses some calculus that you've probably forgotten, and there's lots of ways to ask questions about this. So go ahead, come to class, get some help, and I will see you on Friday, August 23rd, when I'm back from my conference, and I look forward to meeting you all.